be enclosed, but this is not enclosed. Okay, so is there a force on this current? No. Why? Not in the field, right? It has to be in the field for it to be a force. Is there a force down here? What's the direction going to be? Right-hand rule for forces. Take your fingers, put them in the direction of the current. Right? Down here, that's this way. You got to curl them into the field. To do that, I got to turn my hand and curl them into the board. Stick up my thumb, I get a force up. Okay? Do the one up here. Up here, the current is the other way. Curl them into the field, I get a force down. Right? Those two are going to cancel. Right? Remember, we did this when we found out that the net force in an enclosed field is 0. Because everything cancels. So in this direction, that works. These two cancel. What about on this side? Fingers in the direction of the current. Sorry, that's this way. Curl them in the direction of the field. Stick out my thumb. I get a force that way. Right? Not balanced by a force on the other side. These two are balanced because both of these sides are entering the field. This side is not in the field yet, so there's no force. This is imbalanced. Compare it to the direction of the velocity of this thing. What's the direction of the velocity? That way. What's the direction of the force? The other way. We saw this before, right? Magnetic braking is what this is. So we've already figured out that there's no force here, right? What about over here? Same questions. Is there flux? Yes. Increasing or decreasing? I'm sorry. Changing? Yes. Now, increasing or decreasing? Decreasing is the answer. Direction of the field is still into the board. So we've got a decreasing flux. Field is into the board. What does nature want to do? Increase it. How does she do that? Field directed how? Into the board. She wants to increase it, so she's got to line up the field. So over here, I should get a field that looks like that. What direction of current induces that field? Same argument. No force over here, right? This one's not even in the field. If you do the right-hand rule on the bottom leg, you get a force down. Right-hand rule on the top leg, you get a force up. Those cancel. What direction do I get over here? To your left. Yeah, fingers in the direction of the current, curl them in the field, force is to the left. So still opposite the velocity. Take it to the bank, right? If you get a force in the same direction of the velocity, remember me when you accept your Nobel Prize, because that you just got free energy. That's not gonna happen, right? There is a braking magnetic field everywhere. So anytime you have a conducting material, not just a loop, anytime you have conducting material moving through a magnetic field, you're going to induce currents of this nature. Like I said, they're called eddy currents. They don't have to flow around a particular wire. You're going to get currents that set themselves up to flow in this direction. And there might be one here, right? And then one here, and so on and so forth. But the larger the current is, the more it's going to feel this force. So these big currents on the outside get a lot of braking force. All right, let's see it in action. This is a pendulum, right? So this is a really old pendulum. One of the advantages of working at a large and old university, like we have here, is that there's a lot of stuff in the demo room that was machined by guys that really knew what they were doing. I don't know if you guys, as engineers, you should have an appreciation of good machining. A good machine shop is like worth its weight in platinum. And a good machinist is probably worth twice its weight in platinum. We have a great machinist. This was machined way before he or I were born. This is really, really old. But this thing is machined really, really, really well. If I just let it go, it's going to sit there and just swing and swing and swing. Right? It's actually quite a joy to watch. I love this thing. It's just so nice. Machined really well. I'm just going to sit here and do this. Now, what is on the platform are two coils of wire. Right? You can see one over here. It's insulated wire. wire. So we're forcing the current to flow in spirals. These are basically very large solenoids. We know what happens when solenoids have current running through them. They produce a magnetic field that goes right up their axis. Well, on the top of the axes of both of these coils is a large block of steel. That steel serves, it's ferromagnetic, so the magnetic field from the coils then permeates the steel, and basically these serve to redirect the magnetic field. Transformers do the same thing. We'll talk about transformers later. But they redirect the field into the gap in between them, the gap through which this pendulum is swinging. And so the whole purpose of this is to create a magnetic field. I think I said electric, I meant magnetic. That's in this gap, and this thing is swinging through the field. It looks just like that. Because over here it's out of the field, it enters the field. It's never completely encased in the field, but it leaves the field and comes up. The field is here is much smaller than under. But you guys can see it. This thing has been swinging forever. Right? What did I do? I turned on the field. Right? It slows it down immediately. Takes energy out of it. I don't really have the power supply to do it, but you can ramp this up to where it basically just grinds to a halt immediately. It's pretty cool. But if I turn off the field, it's going to go for a long time. Again, this is magnetic braking in a nutshell. So if you're trying to stop a maglev train, like I alluded to a couple times ago, this is a really good thing. But if you're not, if you have other applications that need you to move conducting material through magnetic fields, this could be a real detriment, right? Sometimes you don't want this to happen. So how do you stop this? Well, you don't stop it, right? You can't stop physics, but you can mitigate it. So if you notice, this pendulum is a solid piece of copper. It's like a solid loop up there. One thing you can do to mitigate this effect, I can't show you because I'd have to change it out, it takes a long time, is to cut grooves in it. So instead of a big solid piece, if your application allows you to make something that's like a cone, right? So instead of this solid piece, I get something like this. This has the effect of creating smaller currents. You're still going to get current. But instead of these large currents flowing around the whole thing, you're going to get these little eddy currents that set themselves up like this, right? You're going to get something here, but you're going to get these little currents. Smaller currents, smaller force, right? So this is a practical way to, if you have an application that is trying to mitigate the braking, right, instead of use the braking, if you can cut grooves in it, that usually works pretty well. It doesn't completely eliminate it, right, but it can serve to mitigate it pretty well. So you'll find as you go through your engineering careers that which physics property you want to get rid of or emphasize depends a lot on your application, right? If you have a maglev train, you want to emphasize this. You want to stop it. If you have, for some reason, a pendulum swinging through a magnetic field for some other reason, you might want to mitigate it so you can cut grooves in it, right? This happens all the time. It's an optimization problem. What are you trying to get rid of? What are you trying to do there? Good question. Questions about this? So what are we seeing in this chapter? Well, we've seen a lot of things that are very important to how we live our life. Faraday's law is a big deal, right? Electromagnetic induction is a big deal. Why is it a big deal? Because it's how, I don't know the actual percentage, but it's a really high percentage of how the world's electricity is produced. Solar uses a different effect. Thermistor, if you know what that is, uses a different effect to produce electricity. Pretty much everything else uses different methods to turn a big coil of wire inside a magnetic field, right? That's what nuclear power plants do. They boil water using nuclear fission to create steam to turn a turbine. Hydroelectric production in a dam runs water over a turbine that spins a magnet inside a coil of wire. Windmills spin a magnet inside a coil of wire. This is how the majority of electricity we use as humans is produced. Faraday's law describes that. You have a changing magnetic flux, you get electricity. You can also run it the other way, right? If you have a changing magnetic flux, you can produce electricity If you run it backwards, you put electricity in, you can create forces, well, you can create forces, but really you create torques that then can create rotational motion. So if you're putting in motion, if you're cranking this thing with either your hand or an internal combustion engine or something, or a team of mules, whatever, if you turn it manually, you're creating electricity. But if then you use electricity to make it rotate, you have a motor, right? So you can either put in motion and get out power, you can put in power and get out motion. However you want to do it. It's the same thing. There's a couple design differences, but there's no conceptual differences between a generator and an electric motor. Once you have that, you can then talk about how you induce the magnetic fields induce the electric fields, induce the EMFs, and how the current actually flows, right? And then it becomes an engineering problem how to get the current out that you're creating. But I'll leave that to you guys, right? That's your expertise. Then you deal with things like eddy currents and magnetic braking. It all comes from Faraday's law of induction. An incredibly important concept and set of mathematical equations for our everyday lives. There's one more example I want to show you. Any questions about anything we said just then? One more example I want to show you. This is from a real-world application that was attempted. Producing electricity has been a concern of humanity since it was discovered, really. Since we figured out that we could use it. And a big part of that is, has been trying to discover renewable resources or resources that don't cause harmful byproducts and things of that nature. How you feel about that is not my business. That's politics, not science. But at least in that effort to produce a reliable and cheap, or maybe not cheap, but clean source of electricity, one thing that was postulated was we could produce it in space and somehow get it back to the Earth. Right? To do that, somebody came up with a really ingenious plan. This was in the 80s, or maybe early 90s, but I'm pretty sure it's the 80s. When the space shuttle was in operation. If you've never seen the space shuttle, go look up some YouTube videos of the space shuttle. It was really cool. It was a renewable or a reusable, one of the first reusable space vehicles was the US space shuttle. They retired it in the 90s. It was sort of ubiquitous in my childhood. It was a big deal. But one of the things they came up with was to, as the shuttle is orbiting the Earth at about 8 kilometers a second, that's about orbital velocity, what if they just released a long cable? What would that do? Well, the question is, well, what would that do, and why would it do it? So you have the space shuttle. I'm not an artist, but it kind of looks like this. Small wings. Large. That's terrible, but you get the idea, right? So they would release this cable, this metal cable. Now the Earth produces a magnetic field. All planets produce magnetic fields. The Earth is reasonably weak as when you compare it to things like Jupiter. But it's enough to make your compasses turn around, right? So you can find your way out of the woods if you're a Boy Scout and you're prepared and you have your compass. Alright, so if you drive this piece of conducting metal through the Earth's magnetic field, theoretically, you get a potential difference across the ends. Now, notice I don't actually have a closed loop here. It turns out to just get a voltage, you don't need one. To get a current, you need one. But to just get a voltage, to get a potential difference across the ends of this wire, it's sufficient to drag it through a magnetic field. And if that's all you could do, then this would be an interesting idea, but not practical. But it turns out that space is definitely not a vacuum, right? We think of it as a vacuum, die in a cold vacuum of space, right? From all the sci-fi movies. But there's lots of stuff in space. It's a pretty good vacuum, but there's still lots of stuff. Especially right outside the Earth's atmosphere in the regions where the space vehicles are traveling, there are a lot of charged particles, ions, right? They come from the sun, some come from our atmosphere, most of them come from the sun. But there's this ionosphere. There's a ton of charged particles up there. And what they realized was that charged particles, or ions, are just charge carriers. They're mobile charge carriers, right? You can carry current with just a stream of ions. It doesn't have to be electrons in a wire. So they realized that if they could drag this thing and produce a potential difference across the ends, you could actually set up a current using the ions out here in space. And so the current would flow something like this, right? And and it would come back to the shuttle. It would flow through the wire at one point, and then come back through the ionosphere to get back to the shuttle. And you could actually produce a current in the wire. They tried it twice. There were mechanical failures in both times, but it seemed to actually work. In fact, a couple years ago, I was teaching this class, and we talked about this example, and I said something that wasn't physics wrong. I'm not discounting a possibility, right? But I said something about the mission that was like slightly wrong, and this guy, an engineering major in the back, raised his hand. He was like, "Hey, actually, it was this happened." I was like, "Oh, okay, cool. Clearly, you know more about this than I do." I was like, "I'm just curious, how do you know?" I was like, "My dad was an astronaut on that mission." I was like, "Okay, cool." So he actually gave me all the details. It was actually an arc in the shuttle. The second time, it was actually an arc in the shuttle. If you know what an arc is, it's electricity jumping across a gap in the air, right? So there was current flowing, but it was so much current, it actually melted the insulation in the wire and arced between the cable and its supporting structure and caused a system failure, so they had to shut it down. But it actually worked. It was pretty cool. They were actually producing electricity just by flowing charges through the ionosphere. But even if you don't have an ionosphere, you just drag this cable across, you get a potential difference in the end. If there's no opportunity for a current, nothing will flow, but there is a measurable potential difference. In fact, if you take a piece of metal and arc it through the air in the Earth's magnetic field, you'll get a potential difference across the ends. You probably can't measure it, it's really tiny, but it is there, right? Because the Earth's magnetic field creates this induced potential difference. I always think that's an interesting example. We're a few minutes early on finishing up this chapter, but I'm cool with that, unless you want me to go into the next chapter. All right, so